Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 8-2 Extra Practice Number 2 solutions on geometric series and sigma notation. On this problem, they want us to find the summation from 1 to infinity of 4k squared minus 4. Now, since this is an infinite series, they have a proviso for that. They say just write the first 4 terms, so we're going to take them up on that. So we've got 4 times 1 squared, which is just 1, minus 4. To that, we are adding 4 times 2 squared, so 4 times 4 minus 4. Next, we've got 4 times 3 squared, so 4 times 9 minus 4. And then finally, 4 times 4 squared, so 4 times 16 minus 4. Plus dot, 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 because it's going to infinity. So we can't add all of these together. All right, well, let's go back and just simplify this. So 4 minus 4 is just 0. Next, this is 16 minus 4, which is 12. 36 minus 4 is 32. And finally, 64 minus 4 gives us 60 plus dot, dot, dot. For this one, we're trying to find the sum of nx to the 2n from n equals 34 to 37. Now, the deal here is if you have multiple letters, you have to look extra close at your index to see which letter is actually being having things plugged in for it. In this case, n is receiving all the numbers from 34 to 37. X isn't really doing a whole lot. It's just kind of hanging out and sticking around, and it's going to be in our final answer. So plugging in my 34 for the first term, I've got 34 x to the 2 times 34, so 34x to the 68. Next, we've got 35 x to the 70, followed by 36 x to the 72. And finally, plugging in 37, we have 37 x to the 74. For this problem, we're trying to find the sum, and if it's infinite, we can just write the first 4 terms. So let's start writing out a few terms and see what happens. So I'm plugging in all the numbers, all the integers from 10 to 73 into negative 10k, and then adding them. So I've got negative 10 times 10, or negative 100, and then negative 10 times 11, negative 110, negative 120, and there's an awful lot of these between 10 and 73, so I'm just going to skip to 73. So this is going to be negative 730 at the end, and I'll put a dot, dot, dot in here to show that I left a bunch of stuff out. Now, clearly adding all this up by hand is going to be annoying. This, it turns out, is an arithmetic series. We have a common difference each time here. So I'm going to use my arithmetic series sum formula to do this quickly. That's n times a1 plus an over 2. So for the n value, that's actually the trickiest part of all this. That is the number of numbers between 10 and 73. That's going to end up being, let's see here, 64 numbers. And then for a1, I've got the first term of negative 100. For an, that's going to be negative 730, my last term. So we had 64 terms. Here's the first. Here's the last. Let's just plug it all in this formula up here and see what the calculator has to say. So plugging all that in, we got negative 26,560. And there it is. For this problem, I want the sum from 1 to 38 of 4 to the k. So let's just start plugging things in and see if we can figure out how to do this one. So we've got 4 to the 1, which is just 4, plus 4 to the 2, or 16. 4 to the third is 64, and we're very quickly going to realize that this is going to take us forever if we're plugging all of the numbers from 1 to 38 into the exponent here. So I'm just going to do dot, 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 plus 4 to the 38 to represent that I've got all these terms here in this series. Now, in order to do this a little more efficiently, you might notice that this is actually a geometric series. We're multiplying by 4 each time to get the next term, and the exponential piece here is kind of the tip-off that this is geometric. Since it's geometric, I can use this sum formula, a1 times 1 minus r to the n over 1 minus r. And let me just write out what each of these pieces are. For a1, that's our first term, 4. The common ratio we just said was 4, like 16 divided by 4 is 4. And now for the n, the number of terms between 1 and 38 also happens to be 38. So plugging that in, we've got 4 times 1 minus 4 to the 38 over 1 minus 4, and that is a task for my calculator. Letting the calculator do the very heavy lifting on this one, we come up with 1.007, 007, times 10 to the 23rd. On this problem, I want the sum from -3 to 1 of this absolute value expression. So we're basically plugging in all the integers from -3 to 1 here and then adding it all together. So let's start with -3. We've got -7 times -3, which is 21 inside an absolute value. And then we've got -7 times -2, so 14 in the absolute value. -7 times -1 is 7 in absolute value. And then we have -7 times 0, which is just 0. And then finally, -7 times +1 is -7 in the absolute value. And this is the one where it's really going to make a big difference. So we've got now 21 plus 14 is 35, plus 7 is 42, plus another +7 now is going to give us 49. For this problem, we want the sum from 7 to infinity of this crazy expression. Now the key on this one is realizing that x squared is being treated as a constant. It's just going to kind of hang around. We're going to actually be plugging numbers into the n, not the x, because it says n equals 7. So let's start at 7 here. We've got 2 times 7 times x squared over 5. That's 14x squared over 5. And then we've got 2 times 8, so 16x squared over 5. 2 times 9 now, so 18x squared over 5. 2 times 10, so 20x squared over 5. And we could just keep going, but the upper limit here is infinity, so we only had to write the first 4 terms followed by a plus ... to show that it's infinite. For this problem, we're trying to write this series using sigma notation. So let's see if we can find kind of a formula for getting each term of the series. These are all multiples of 11. So when I write out my sigma here, I can write 11n as my summand. And then the first term here, this is really 11 times 1, so I can write n equals 1 for the lower limit of summation. And while the upper limit, it's not 4, right? This is a plus ... so that means infinity is going to be our upper limit here. For this problem, we want to write this series using sigma notation. We notice that these are all powers of 1/3. So when I write out my sigma, I can write 1/3 to the n or 1/3 to the n. Either of those are the same. And then for my lower limit, I'm starting with 1/3 to the first power to get this 1/3 here. So I have n equals 1 as the bottom. And for the upper limit, this plus ... is telling us that this is an infinite series, so infinity is my upper limit. On this problem, I want to write this series using sigma notation. So let me start with the common pattern here. These are all x's inside some kind of root. So when I'm writing out my sigma here, I'm going to have an x inside a radical. And then I'm going to have to make sure that my index variable is not x. So I'm going to write this as the nth root of x. And now I just have to make sure for my lower limit that I have a number that lets me start with this first term here. To get this first term, I would need to plug 5 in for n. So I'm going to write n equals 5 for my lower limit of summation. And now for the upper limit, this is just going until we get to 8. So 8 is the upper limit.